Right, good morning everyone. We're about to finish chapter 5. This is our last section, and we were finding inverse functions, and one application of inverse functions is here. A camper is hiking down a steep path, and we already know how elevation of the path is 560 yards. And we know how long this hiker is moving on this path, 1,350 yards. We're just wondering how steep this path is by finding the theta that makes angle with the ground level and the hike path. Okay, so this theta is asked, but this is nothing but finding one angle in a triangle. Everything has been set up for you in the picture, but here is the story if you're interested in reading it. Okay, so hypotenuse is 1,350. One of the legs opposite side is 560. We are wondering the theta. So hypotenuse and opposite side given, guess which function we are gonna use? Sine. So to find out theta, we need to relate theta into 560 and 1,350. That's sine, which is opposite over hypotenuse. The opposite is 560 and hypotenuse is 1,350. So you have this, but we know we can't figure this angle out like that. But do you know what angle makes sine? I mean, I can divide both sides by 10. Which angle 30, 45, 60, 90 makes 56 over 135? Is this one of the common values in the table or the wheel? No, then you're stuck with using a calculator. So for this, I flip theta and 56 over 135. I put 56 over 135 to the left and theta to the right. Can I just do that like that? No, you can do that if you invert the function. So this is sine inverse of 56 over 135 is theta. We will just punch in this into our calculator and get the result. So for Google, use arcsine 56 over 135. That's radian. I believe they don't want radian value. Always arcsine is measured in radians, so you need to convert that into a degree measure, and a radian is changed into degree if you multiply it by 180 and divide by pi. Doesn't change. No, it says radian, but it's no longer radian. Google is not that smart. Okay, the answer you found here is not radian, it's the degree. It's 2457. So which is the precision amount? Nearest tenth. So nearest tenth is 24.5. So that's how much that angle is. I mean, this is a very common question, especially if you're a builder and you want to find out how steep a side is. That's what we use as well. Especially you want to have a perfect corner if you're building walls, and you want to get a 45-degree angle here. I mean, if you don't have a compass or stuff to measure that angle, so you just look at the sides ratio, and you can compute sine and cosine, or even use Pythagorean theorem, see if this is 45. Okay, so these are some applications you can use. Alright, yesterday we only mentioned 3 inverse functions: sine, arcsine, arccosine, or arctangent. It's not fair to skip secant, cosecant, cotangent, but they are pretty much the same as the first 3. For example, secant actually is, alright, lost that one, my pen. But what is the definition of secant? What is secant? Isn't it 1 over cosine? So you expect secant and cosine, arc secant, arc cosine be similar. Remember yesterday, so let me run this again. Arc cosine was limited to a range of what values? Arc cosine was minus pi over 2 to pi over 2. No, that was arc sine. Arc cosine was 0 to pi, right? Let's check out arc cosine again. Where are you, arc cosine? Here. Arc cosine has only values when somebody asks you to evaluate it from 0 to pi. So you need to provide me an angle between 0 to 180. And arc sine was minus 90 to 90. Any value of arc sine is within this range. Secant is just like cosine. So I expect it to be 0 to pi, except it takes a break at pi over 2. You see, it says 0 to 90, and then any value after 90. You are skipping the value exactly 90, because secant is actually not defined at 90. So we are skipping the value at 90 again. All right. So from 0 included, 90 excluded. You see, strict inequality. We don't reach at 90, and then we continue after 90. We are not stepping, never stepping on 90. So secant is just like, arc secant is just like cosine inverse. However, the difference is cosine inverse is entire range of values from 0 to 180, but secant inverse is skipping that 90, right, the middle value. Same thing happens with cosecant. Cosecant is just like sine inverse. They act like sine inverse, same values, except sine inverse used to be from minus pi over 2 to pi over 2, but cosecant inverse is skipping the value in the middle. 0 is skipped. You're going up to 0 and then skipping 0 and counting more. I don't want you to memorize these pictures again. I'm just giving you so in future when you see them, don't be surprised. Okay? But what is important for me is when you're finding cosecant and I give you a value, I supply you this value, don't give me a radian value like 3 pi over 2. No. It's limited to minus 90 to 90, no 0. And don't give me a value like 0, because cosecant never becomes 0. Okay? Same thing valid for cotangent. Cotangent and all is actually just like cosine, or cosine inverse, or secant inverse. So these three are very similar. Cosine inverse, secant inverse, and cotangent inverse, they all lie on the value from they change from 0 to pi only. Cosine inverse, secant inverse, cotangent inverse are all 0 to pi. These are entirely 0 to pi. This one skips pi over 2 though. Okay? How about the other ones? Sine inverse and cosecant inverse and tangent inverse. These three act similar. This is again from minus pi over 2 to pi over 2. This is minus pi over 2 to 0. Right? This one is minus pi over 2 to 0. Or 0 to pi over 2. Which one was it? Which one did we take? Minus pi over 2 to 0, right? No, 0 to pi over 2. Sorry. So these are not the same. Tangent inverse is kinda standing alone. Let's double check. I wanna make sure. Should be. No, it's the same. Yeah, minus pi over 2 to pi over 4. Yeah, the picture of tangent is like that, right? So they are the same. I confused myself. So they are all the same. Oh, this one, however, doesn't attain that end values. Tangent at 90 or minus 90 is undefined, but sine is well defined. Cosecant inverse, however, is skipping the mid value. Skip the value at 0. We don't know cosecant at 0. But other than that, minus pi over 2 and pi over 2 up to pi over 2 is fine. So these three are a group. These three are another group. Okay? Alright. Number 13 and number 14 are just calculator questions. I'm not asking anything difficult here. Just what is cosecant inverse 5 over 4? You just need to punch this in up to, and round it up to 4 decimal values. Okay, I will just show you how it's done, and then you're done. Arc. I'm not sure Google can do it though. 5 quarters. Yeah, 53.1301 is the answer for this one. And I don't even take the last one, but I think that's also calculator question. Alright, most widely used inverse functions are the first three we investigated yesterday in detail. Arcsine, arccosine, arctangent. Arcsine and arctangent runs from minus pi over 2 to pi over 2 again. I don't know how many times I told this. And arccosine is 0 to pi. Okay? Alright, so this is all in chapter 5. The beginnings, fundamentals are over. Now you're a master of evaluating trig functions at given values, finding their inverses, you know their graphs, you know some basic trig identities, right? Sine square, cosine square 1, right? Reciprocal identities. Now we're gonna go to the next step. We're gonna start proving relations between identities, creating new identities, showing that actually that identity is similar, actually exactly the same as one of the old ones we have seen, and using old ones, creating better ones, that sort of stuff. That's in chapter 6. Any questions? Alright, analytic trigonometry. Then we will cover 5 sections here. We will first employ trig identities to build newer ones, see their relations between them, and then in the remaining sections we will build more and more formulas, more trig identities. So you're gonna have a whole page of list of identities, unfortunately. And the way, I mean, you will understand them of course when I explain them, but the way to master those identities is practice, practice, practice. Okay, so don't be just feel satisfied by the problems I put on homework. Just go extra. Hit the practice more button, do textbook questions as well, until you feel comfortable. Alright, you should be able to prove an identity or solve a question under 5 minutes. Okay, then you will know I'm good at this. Okay, now pretty much 6.1 we are reviewing past stuff. Okay, but to do challenging things, proving things, math questions, identities will be proved here. So old stuff revisited. So this is another chance to fill in those gaps. But we will do really nice proofs. So let's review what we have in our toolbox. This is our toolbox. Keep this ready when you're working on homework practice questions and these questions as well. First identity, set of identities we have observed is reciprocal. Reciprocal identities, like 1 over something is called reciprocal, right? So like cosecant is 1 over sine, secant is 1 over cosine, cotangent is 1 over tan, tangent is 1 over cotan, cosine is 1 over secant, sine is 1 over cosecant. Look, you can kind of flip these two. Okay? Tangent, the other list, second group is quotient identities. It's tangent and cotangent only. Tangent is sine over cosine. Cotangent is cosine over sine. The third group coming in, again, these are not new, right? You have already seen these before. Maybe we didn't mention this relation, sine and cosecant relation directly, but you can flip these two sides and get that one. Flip this side, 1 over cosine, cosine, secant, 1 over secant. Okay? The third group, as we mentioned, is Pythagorean identities. And there are 3 kinds, but this is the most widely used one. Sine square plus cosine square, when you add square and add them, they make perfect 1. Tangent square plus 1, when you add 1 to tangent square, it turns into secant square. And 1 plus cotangent square is cosecant square. Again, don't feel these will be used in the given format. No, sometimes you may want to subtract this and use tangent square equals secant square x minus 1. You may need to use this side sometimes. Or sometimes you leave sine square alone, subtract cosine square from both sides. You make sine square into 1 minus cosine square. You use it in that format. So be ready to manipulate this given order into a newer one, the format that is useful in our application, whatever the question is. All right, and the last one is called even and odd function properties of trig functions. Except 2 out of 6 trig functions, except 2, all trig functions are odd functions. In other words, when you have a minus inside, that minus comes in front like this. This minus comes from, except 2 of them I said. Which 2? Cosine and secant. Cosine and secant simply wipes off these minuses. Minus just disappears in cosine and secant. The other 4 is just moving the minus, kicking the minus out. Keep that in mind, it will show up, okay? Again, which 2 are even, which 4 are odd? Secant and cosine even, that means minuses disappear. But the other 4 are odd, means minus goes out. Okay? Alright, ready for our first question now. Well, we'll pick one or more tricks here, identities, and use this in this mess. Look at the mess. To do what? Simplify. You want to get as much junk as possible here. There are 3 trig functions multiplied here. Look, they're all multiplied. And one of them is even square. We are gonna change them. Use some identities from the top and get this as simple as possible. Preferably just single or 1 or 2 trig functions remain. All those maybe squares go away as much as you can. So I need ideas. Which one of these can you change? How do you change? What do you change? Right now, do you see any cancellations? Do they cancel secant, cotangent, and tangent? No, there is nothing common, right? to make cancellations, I believe we need ratios, numerator and denominator, so top and bottom can cancel. So it's a good idea to change tangent, cotangent, and secant into ratios. Maybe you want to change secant into this, tangent into that, cotangent into that, right? Look, secant is 1 over cos, tangent is sine over cos, and cotangent is cos over sine. So you have something on the top and bottom, and kind of similar items, sine and cosine everywhere. Probably we can cancel them, right? So why don't we change tangent first? Tangent becomes, what is tangent? Sine x over cos x, right? Secondly, cotangent squared, which is, what is cotangent? Cosine over sine. And lastly, secant. I'm missing something and nobody is aware. Yeah. This cotangent was squared, so you need to create squares around this. By the way, this is what I prefer. Usually we are expected to put square here, right? But in math, you can move this square to the top of the S, like here. It's more compact, it's more suitable for us instead, because otherwise you need to make all the time these parentheses. I don't want to waste ink. Okay, so that's why I just move this. I mean, we move, this is tradition, we move the square to the top of S to avoid parentheses. But why do I need a parenthesis? Can't we just skip parentheses and put the square like this? Can't we? No, because this reads as cosine of x squared. Double x. No, that's not what I mean. This is wrong. We mean cos x times cos x, right? So this is wrong. This means cos x times x. This is x times x if you put that square there. So you either use parentheses, but if you don't want to use parentheses, move the square to the top of S. That's one tradition we do. Alright, next. Yeah. Secant is not 1 over secant, of course, it's 1 over cosine. Alright, what do you see next? We get my different color. We are going to cancel things, right? I see sine and sine matching, but this is double sine, so there will be one sine left here. I see cosine and cosine canceling. There is another cosine left, but that cosine is killed by another cosine. And what is left? Here, if everything wipes out, there is still one everywhere. 1 times 1 times 1 times 1. On the top you have only 1. 1 times sine times 1 is, what is it? Just sine. Can I leave my answer like this? I'm kinda okay. You kinda reduced it. But don't we know 1 over sine is something we very well know, which is cosecant x. I'm just curious if the system is gonna like 1 over sine though. Let's try 1 over sine first.
This is right the final form of the fractions.
Oh, okay. Alright, first step in solving these questions, read the statement. Okay, so I'm not, so you saved me time, so it's cosecant x is the answer. Oh, there are buttons for this if you don't want to type in, but I think this will be fun. Alright, we're coming to the next one. Write the final form with no fractions. Sure. Again, if you need this table, I don't. If you need this table, keep it on the side, alright? Or we may need it now. But at this moment, You must know all these identities by heart. You shouldn't be needing this, okay? What do you think we're gonna do? You can go with elimination. I mean, I don't see any minuses here. I'm not gonna use this. I don't see any tangent, cotangent yet. I don't use this. I don't see secant or cosecant. I don't need any of these. Wow, you don't have much left. Well, I see some squares. I don't see any much use. So we need to prep the question first for this table. Right now, the current table and current format it's not getting us anywhere. So Kylie says this doesn't have a denominator. This has a denominator. Why don't we add these up first by multiplying this top and bottom by cosine x? So I will multiply top and bottom by cosine x. So we can have a common denominator between these two fractions. This fraction will have a common denominator. Look, again, sine square x plus 1. I didn't do nothing to the first one, so I'm just copying it. Copy the first one. The second one now becomes becomes cosine square. You have a match. If two denominators match, two ratios have common denominators, we can combine them into one and add up the tops. Good. Next.
You combine the sine and cosine.
Perfect. We can combine these guys, right? Correct? Sine and cosine square makes 1. This one. So you already have a 1 and another 1 coming in. Okay, so it is 2 over cosine x now. And they say no fractions. I still have a fraction. Yeah. This is twice 1 over cosine x. That's 2 secant x. Alright, you're done. Good. Wow, this is even messier. In case you may need. Alright, I don't have any negatives in the trig function, so I covered that. All you need is this. Take a moment. One idea is to change cotangents into cosine over sines. Alright, so this one will turn into cosine square over sine square because it has a square everywhere. For cosine over sine and for cosine x cos x over sine x minus 2 cos x. Okay. That's my start value. Don't write it. We don't know it's the right way, okay? Maybe it's gonna be a dead end. We will go push and as long as we can go, but maybe dead end.
You can combine the cosines on the bottom.
Yeah, we can make this cosine squared. Can I do it right on the spot? Good idea. So can I just change this into squared like that? Okay. Great idea. We may want to multiply both top and bottom with sine so that all the denominators with signs may disappear. However, is this single sign enough to cancel the square? So why don't we multiply by sine square? So sine square and this cancels to cosine square only. And this will make multiply. One of the signs kill each other, but there is a leftover sign here. Sine and cosine combines. Cos x, sin x. And this has nothing to kill in the denominator, so 4 and sine square becomes 4 sine square. Alright, here one sine kills, the other one remains, so sine x cos square x minus 2 sine squared cos x. Oh yeah, this is what we have.
You can cancel the sine x on top and bottom and then make up sine x squared.
You mean something like this?
Yeah.
Well, technically no, because there are things added or subtracted to it. I mean, this is multiplication. I wish these were not here. Then you could cancel these signs. But if there are other items added or multiplied to the top and bottom, no, you cannot cancel them unless you can factor a sine x. If you can factor a sine x from each and everybody from top and bottom, call it outside, then yeah, you can cancel, but no. Oh, I can factor a sine x from these guys, right? I can. But this doesn't have sine x. This has 1, this has 1, but this has no sine x, none. So you cannot factor a sine x, guys. Are we stuck? Do we quit? Kyle, do you have any input? Any ideas? You're ignoring one skill, one trick we use to simplify things. For example, how do you guys simplify this thing? How? How do you guys simplify such a thing? we factor. This is x minus 2, x minus 2. Oh, there is an x minus 2 here. Bam, bam. And then we have something simpler. Do you see something like that going on here? I just wanted to sweat on this like this. This, by the way, can be done. It works. But it's just longer. You need to factor it here and cancel stuff. It works. But I don't want to pursue this anymore. It's just taking longer than this. Try factoring top and bottom just like this. Imagine this is u squared minus 4u plus 4. How would you factor the top? U squared minus 4u plus 4. U's is cotangent x. I already gave you the answer actually. It is u squared minus 4u plus 4 is u minus 2u minus 2, right? What is u? Cotangent. Okay, I factored the top. Well, how do I factor the bottom? I don't see anything factoring there. Do you? Do you see something coming you can call out? Cosine. Cos. And I factor cosine. It's cotangent x minus 2. Look at this. These are a match. They cancel. It is cotangent minus 2 over cos x. Okay, what is next? Now let's do what Kyla said. Cotangent is, because I need something common. Cotangent is cosine x over sine x minus 2, and this is cos x. And I will set these denominators the same, sine x and 1, and combine these two. So to set sine x and 1 the same, I need to multiply this one, top and bottom, by sine x. Well, it's not happening. I was gonna cancel out this, but it's not happening. Any ideas? I changed my mind. I'm not gonna. I mean, you can do that. It still works, but no. Let's quit this. I have a better idea. Yeah, I will still call this. So, what is our goal? We simplified this, but they don't want no fractions. I still have one. Here is what I'm gonna do. I will break this into two pieces. This top. Now I'm gonna separate each fraction. Do you see that? Can I do that? Like 2 plus 3 over 5 is 2 over 5 and 3 over 5, or 2 minus 3 over 5 is 2 over 5, 3. So you can distribute a denominator to each term on the top. Okay. Alright, so that's what I did. And then cotangent, isn't cotangent one of cosine over sine? And these are gone, right? Agree? And what we have in the first one is 1 over sine x. Second one is twice 1 over cosine x, and I'm stuck. I can't move anymore because we are almost there. What is the final move? Again, we shouldn't have any ratios. I see fractions.
1 over sinus cosecant.
Right, this is cosecant x. 1 over cosine is secant x. Cosecant x minus 2 secant x. This is how much we can go. Alright? All the steps we did earlier attempts yield the same answer. If you go, don't stop and go, continue, you will do it. I mean, even the first method we did, cotangent over sine, but you just need to combine more denominators, add, subtract. They will eventually get there. But this is my approach, alright? Cosecant minus 2 secant x. Alright. Challenging, huh? I mean, yeah, that's how it works. Now, format of the questions changed. Alright, who can tell me? No, not that one. Who can tell me, compare number 4 to 3, tell me what is different. 3, 4.
The x's are minus.
We have minuses inside, okay? So that means we are going to employ somewhere this bottom rule, even add odd identities. That's one minor change. There is a big change in the format of the question.
You already have it, it's equal to.
Yeah. This time we are not just simplifying. Look, it's a show that type of question. Prove that. Demonstrate that type of question. You have something on the left hand side. This is called left hand side. Left hand side. You have something on the RHS. What is RHS? Right hand side. Two trig identities or trig equation expressions on the either side. You are going to, what is this? Prove they are equal. Prove or show they match, they are equal. This is a complete different type of question. Here, we were only changing this into simpler looking things. There wasn't left, there wasn't right. Only there was a left side. You continued and continued until you get something simple. Here though, you have two sides already been given set equal. We don't know if they are equal though. This is a big question mark. Maybe they are not. They won't match and we will say no, it's not a true identity, it's a false identity. So don't assume they are the same. We are going to start one side and reach out to the other one. That's how you show it. So let's read the strategies for this kind of questions. Again, you are completely free to pick, I say pick one side. You're gonna go with LHS or RHS. You will pick one side first, okay? It's your choice. But there are help, of course. You're not randomly choosing them. You're not gonna toss a coin, okay? We pick usually the more complicated side, more stuff, more juice. Wherever you have, you start with it. For example, which side would you start with in this question? Come on, which side makes sense to start with? But which side would you pick, left or right? Left. You have more juice, more Play-Doh on the left. You can form more things on the left, right? Okay. Alright, a lot of canceling, killing can happen on the left, so we pick the left side. It's more fun. Okay, I understand the strategy one. Pick a side, go with the crowded side. I did. But sometimes it may not work. Sometimes some tricky questions may have the easy part working for you. Alright? Look for opportunities to apply fundamental identities. Again, you're going to use this table. Look for opportunities. What kind? For example, use product and quotient of factors. Consider reciprocal and quotient identities. You may need to flip tangent into sine and cosines. Cosecant into 1 over sine. Okay? cosine into 1 over secant. You may wanna flip things. Okay? You may wanna use Pythagorean identities. So group sine square and cosine squared somehow. You may need to use this or that. What else strategies we may use? If there is a negatives, like this, you may want to use even and odd properties. This is maybe the easiest to apply, because 4 of them are odd, 2 of them are even. Okay? And not only that, sometimes you may need to factor. You will factor this, right? You may need to factor sometimes. We may need to factor multiply terms. You may need to multiply cosine and cosine maybe. Combine like terms, like 1 plus 1 is 2. And you may need to write common denominators. Haven't we done common denominator work here? We got the common denominator and combined fractions. I think one important trick it's applied all the time is missing here. Let me add it to here. This is so essential. You may need to sometimes multiply by conjugate. Do you know what conjugate means? No, that's reciprocal. That's reciprocal. So if you have x, 1 over of it, this is called reciprocal. Conjugate happens for binomials or 2 items like x minus 3. What is the conjugate of x minus 3, for example? Conjugate x and 3 with a plus. What is the conjugate of x plus 3? X minus 3. What is the conjugate of cosine x minus sine x, for example? What is the conjugate? Yeah, you just flip the sign in the middle actually. Why would you need such a fancy name for it? But they did it. So flipping the sign between 2 items, addition or subtraction, whatever is given, you're flipping it onto opposite. It's called conjugate. This is the conjugate of cos x minus sine x. Alright? So this is used a lot. I have a feeling it's gonna be used here. Okay? And yeah, sometimes you may need to change tangent, cotangent, all signs into cosine as well. Example here. Question 4 will definitely need that to be done. Alright, here is the strategy we are gonna use. First, pick a side and start with it. We said we agreed on left hand side, right? So write this. I really want to see this. LHS. Write with this, write this, and copy what do you have on the left side. Use some, and then keep working. Keep working using tricks, identities. I want to see a lot of work here, but when are we over? When are we done? Once you get the right hand side term, minus cosecant square x, which is the right hand side, it's over. Stop. I need to see reasonable, mathematically right moves in the mid-step. Do flip things, cancel things, combine things, get common denominator, whatever you do, I don't care. On the very end, I want to see minus cosecant square. Some people sometimes cheat. They put this here and then do some bad algebra here, but makes no sense. And here I've proved it, but that's not true. You need to, from one equal to another equal sign, everything must be mathematically right operations. Alright, so you know what to do. What do you want to do first?
Get rid of the minus sign?
Yes, we never like the minuses inside. Get rid of them. And we know, except cosine and secant, everything is odd. Means minuses comes in front, but except secant. So secant will take care of this minus. So this minus gone. Because secant is even, right? So we don't have any minus here, so I'm not touching cotangent. So what happens to minus to tangent? Minus of the tangent? It comes out because tangent is R. Cool. Next. What's that? Expand the square. How? Which square? Secant square? How? Yeah, this is secant x times secant x. Okay. Cotangent, you want to flip the cotangent into... Yeah. It's a lot easier if you work with sine and cosines. Change here everything into sine and cosines. Like secant is 1 over cosine, but when you square it, it's cosine square, right? This one is this guy. Cotangent is cosine over sine. Tangent is okay. Do you see any cancellations? Yep. 1 cosine, 1 cosine. There is another cosine left though. Anything else? Yes, we can. We can cancel 1 cosine here. These green ones cancel because they are on the same side, both in the denominator. I have a better idea. Why don't we cancel sine and sine as well? Can I cancel those? No. This is in the numerator. This is in the denominator of the top. Wrong. They don't cancel. So let me rewrite what's left here. 1 left, sine x left, sine x left. This is 1. So 1 times 1 is 1. 1 times sine is sine x. And on the bottom you have only minus sine x. How do I combine this? Let me show this one. I don't know why, but I want to show that denominator one. How do you combine that top and bottom? If you have a fraction divided by another fraction, the way you combine is multiply by flip. We flip and multiply. Flip and multiply. So it is top is the same, but the bottom comes 1 over minus sine x and multiply. Flip and multiply. Oh, 1 times 1 is 1. Sine times sine is negative sine square. Alright. I'm still not there. When do we stop? Can I call this minus out here? Right. This thing is, yeah. This thing is, actually I can call this square out here. This square moves out right here. Because 1 times 1 is 1 again. I can make even a square if you wish. 1 times 1 is still 1. And I call these squares out. 1 over sine is cosecant. And done. Look, you got it, right? So if you stop here, you won't get full credit because I don't see the right side. Don't stop there. You need to give me the exact match. You have successfully proven that these two are equal. Okay? That's how it goes. It's all combining your smarts and what you learned so far. There is nothing new. All your math knowledge is put into work actually. Alright, you guys start this one. I'll give you a couple minutes head start. Pick a side, work on it. So we pick the left hand side, which I see two fractions. Well, what did you do with these fractions? That works, but you can change cosecant into 1 over cosine, 1 over sine, and then work there. But before that, look, do you see any fractions on this side? This is where we're trying to go. I see fractions, two fractions especially. Why don't we try to combine and make one fraction first, and then we get to no fraction part later. Our first task is if you have multiple fractions, make them one. And how do you guys make one fraction? You need to have common denominators. So are they have a matching denominators? Is this factors the same? No. So we need to multiply left side and this one and that one with something. This one requires 1 minus cosecant x, 1 minus cosecant x. This one requires 1 plus cosecant x. It's actually conjugate of these things are alright, right? 1 minus cosecant, 1 plus cosecant, they are called conjugate. Let's see what we get if we do that. 1 minus cosecant x over, alright, what happens when you multiply these two? 1 minus cosecant, 1 plus cosecant. Do you guys know this trick? A minus b, a plus b. Isn't this a minus b, a plus b? A is 1, b is cosecant. What's the quick way to multiply it? You can FOIL it, but quick way is a squared minus b squared. So this is 1 squared minus cosecant squared. Top is 1 cosecant x, and the bottom is again 1 minus cosecant squared x. Now can I combine them because they are the same? Common denominators match, so I'm combining them. The top will add up to, but this is minus. I'm marking it red. Careful. So we will subtract these items from that group. Minus 1. There's a mistake. Yes. This should be minus. Do you all see that? Because when I subtract 1, it's minus 1. Okay. But when I subtract cosecant from this group, it's minus of all this stuff. This has to be minus as well. Now, combine like terms. Aren't these like? Actually, they cancel, right? They cancel. These are like, they are the same. So can I combine these two? Make how many? Minus 2. Okay. Now, it's one single fraction. I need to lose it. Here is the time to change cosecant into 1 over secant. Let's do it. Okay.
Isn't a squared like the
Oh, yeah, yeah, thank you. Yes, important mistake. Alright, now I need to combine these fractions. To be able to combine them, you need to first combine this. Combine. This is already one fraction. You don't have to combine this. It's actually. Can I move this minus 2 to here? Okay. Alright, to combine this one though, I will be quick. Sine square is needed. And look what's going on. One of the sines gone. And we have minus 2 over sine square x minus 1 over sine x. Now can I flip and multiply? Can I? Yes, let's do that. And I'm stuck, guys. I can't move anymore. I need help. I couldn't get it. I have no clue how this turns into that. Again, where are we going? Always don't lose sight of what your goal is. This is my goal. I need to get tangent and secant, and I don't see anywhere tangent and secant. I'm in a dead end. Hint. This is hint. What's that? Alright, you're close. The bottom is, move this guy here, move that here. Look, you have the bottom. Sine square x minus 1 is minus cosine square x. So this guy is minus cosine square x. Alright. So what? Oh, by the way, minus and minus cancels. That's okay. What is our goal again? Tangent secant. I need to get 2. Alright, I got 2. Good news. You already had one piece matching. That's an improvement. I need to get tangent and secant. How do I get tangent and secant from this?
Can you take one sine for the cosine?
I can try that. You mean like this?
So like one of the sines will come away and come out of the cosine. Like,
Oh, okay. You want to take one of the cosine out. This is cos, right?
yeah, maybe two.
So you want to group these together like that. Then what do I group them? What do I do with this leftover? Yeah, group this one with as 1 over cosine, because everything can be multiplied by 1. So you're separating this cosine from the other group. I see where you're going. This is 10 and this is secant. Good job. How many tricks we've used? I lost count. So go ahead and go home and try this question on your own. See if you can do the same work.